So here we're going to give a definition of serial and parallel manipulators. So another word for serial manipulators is the manipulators that are open loop chain. What does that mean? It means that in between one joint to the other joint, there should be only one link. That's one thing. The other thing is that in open loop chain manipulators, you only can see one path going from the base to the end effector. But in parallel manipulator or the closed loop chain, as you see here, this is as an example, there are 3 different paths going from the base to the end effector. So, as I wrote here, every link in the kinematic chain is connected to any other link by at least 2 distinct paths. Okay? So that is the definition of serial and parallel manipulators, as you see here. And now we have hybrid manipulators. Hybrid manipulators are manipulators that they have both open loop chain and closed loop chain. They're a combination of both together.
Your fingers are open loop chains or closed loop chains?
Fingers.
Yeah.
Fingers.
Are open loop.
Is this open loop or closed loop?
This is not closed loop chain.
So, right?
So imagine my body. If I fix both of my feet to the base, and I can't move from here to here, imagine it's fixed. Now my feet are closed loop chain, they're parallel, but my hand is open loop. So I am a combination
This
of...
is closed loop.
This is closed loop, exactly.
So it is this, you cannot say it is permanently anything open loop or permanently closed loop, so how it is coupled. So when you do bimanual grasping or something, when you're driving a car, your whole thing is closed loop, right?
Yeah.
Because one movement affects the other, and it is a collaborating thing.
But does closed loop essentially mean parallel?
No. Closed loop is
Closed loop
serial.
is like from one base to the other base.
Okay.
There's a complete path.
Let me show you here. We have fixed base here, okay? And we have one end effector. In between the base and the end effector, how many paths do you see? 1.
Yeah.
But in between this base and this end effector, how many paths do you see? 3. So there are 3 different paths. Now if I remove this end effector, then each one of them is a serial or open loop chain. But if I connect them together, they become parallel robot or closed loop chain. They're being closed in another word.
So what's the relation between parallel, serial, closed loop, open? How are they related?
Serial or open loop?
Serial robots?
I wrote
Or
here,
always
serial
open?
manipulator is open loop chain,
Always.
always.
Okay.
And parallel manipulator is closed loop chain.
Always.
If you look at it, they're all reaching to one point and they're being closed, being fixed to each other. If you look at it word-wise, a combination of serial manipulators reaching to one point from one base to one point, they are closed loop chain, in another word, parallel. This is parallel to this is parallel to this. If you even look at the meaning of the word. Is it fine with you now?
I'll think about it.
Okay. So I'll go to the next slide. So we want to give explanation to degrees of freedom. If you want to look at the very, very easy definition at it, think of degrees of freedom as different ways of making different motions. Each motion itself is 1 degree of freedom. If I move up and down, it's 1 degree of freedom. Left and right, 1 degree of freedom. In and out, 1 degree of freedom. Rotation, 1 degree of freedom in the angle. And in this axis, rotation in that axis, rotation in that axis, each one of them is 1 degree of freedom. So every motion is 1 degree of freedom. Okay? For example, imagine a servo motor. Tell me what is the degree of freedom of a servo motor? 1 degree of freedom because it's only rotating around one axis. So it's 1 degree of freedom. And a a sliding part. Imagine I am sliding this paper in this direction. This is 1 degree of freedom, okay? And everybody in the space, a 6 degree of freedom space, everybody has 6 degree of freedom. Why? Because we have 3 translational motion, one moving in X direction, I'm just translating without rotating, one translating in Y, one translating in Z. Okay? So these are 3 translational motions in X, Y, and Z direction. So what about the other 3 degree of freedom? The other 3 degree of freedom are rotational. Okay? So we can rotate around X, we can rotate around Y, and we can rotate around Z. Each one of them is one motion. Okay? So in total, we have 6 degree of freedom. 3 translational motion and 3 rotational motion. Okay? And as I said before, every robot has its own specific degree of freedom with respect to what motions that robot is able to do. And the formula for the calculating the number of degree of freedom is this formula, where I'll explain each one of them one by one. N is the number of links. Links are what are connecting 2 joints to each other, as I explained before. So the number of links is N, but sometimes we have 2 different formulas for calculating degrees of freedom. Sometimes they don't count the ground as a link. Sometimes they count the ground as a link. In this formula, the ground, the base itself, is also counted as a link. Okay? So you will count that too. K is the number of joints. How many joints do we have that they are connecting the links to each other? Fi is the number of degrees of freedom of each joint. I will explain the type of joints, and each one of them has how many degrees of freedom. Okay? For example, sliding is 1 degree of freedom. Imagine we have a robot that has 2 different joints. One spherical joint, which I will explain, one sliding joint. Okay? Imagine the sliding joint is the first joint. So we say the first joint has 1 degree of freedom. Okay? If the first joint is a sliding joint, we say the first joint has 1 degree of freedom. So Fi is the number of degree of freedom of ith joint. And imagine the second joint is spherical. Spherical joint is like this. Look at my finger, my hand. Spherical joint is like this. Okay? So it has 3 degree of freedom. So we will say the second joint has 3 degree of freedom. So Fi would be 3. Okay? And what we call this, lambda? Lambda? Okay, lambda depends on the space that the robot is in that space, okay? If the robot is in the 6 degree of freedom space, lambda will be 6. If the robot is in a 3D space, lambda would be 3. This way, you will be able to calculate the number of degrees of freedom. Okay?
Shall we do it for tooling manipulator?
Tooling manipulator. So,
Planar tooling.
let's say this is 1 degree of freedom, this is 1 degree of freedom. Joint 1, joint 2, and effector. Okay? So,
Lambda is 3 because it's planar.
yes, lambda is 3. And n, number of links, we have 1 link, 2 link. So n would be 2. And again, lambda, we know it. K is the number of joints. We have 2 joints. 1 joint, 2 joint. K would be 2. And lambda, we know it. Fi. So F1, I don't know if you see it.
Wow.
F1, degrees of freedom for joint number 1 is 1. It's only rotating this direction. And F2, degrees of freedom for joint number 2 is what? 1 again, because it's only able to rotate in 1 direction. Okay? So the formula n is equal to lambda is 3 because we said the robot is in a 3D space.
Plane space.
Yeah. N is 2, which is the number of links, minus 1, minus K is 2, start from I equal to 1. Where should I write? Okay. 3 minus. Let me.
That's fine. 3 minus 1.
Yeah, I wanted
Add
to.
it.
Okay. 3
Consider it as
minus
4.
1. Let me just erase this and then just write plus. Okay, anyway. And then the other one is also 3 minus 1, which this would be 2. 2 minus 1, 1. 3 multiplied by 2, the 1 is 1. 3 minus 2 is equal to 1. So number of degrees of freedom is 1.
No.
Wait. No.
So you have
two.
lambda minus fi is 2. 2 times 2 is 4,
Yeah.
and minus 4. Then
Oh, I wrote, okay. 4.
should be minus 4.
Set down. No, it would be 3, but no, it would be minus, no.
No. So your lambda,
Lambda is 3, number of links is 2, number of joints is 2. Wait, we didn't count base. We didn't count base. Base is
Shouldn't
with
there be a
base.
plus sign between the first term and the second term?
Number of links is n. Base should be 3. Because we have 2 links and we're also counting base as a link 2 in this formula. So this should be 3 minus
Yeah.
1.
and then minus
It will be
4.
6
Minus 4.
minus 4 is equal to 2. So number of degrees of freedom is 2. If you look at here, we have one joint is rotating, 1 motion, one joint is rotating, 2 motion, it's 2 degrees of freedom. With the formula, we also can calculate 2 degrees of freedom.
Cool.
Okay? Fine? So next slide. Now I'm going to explain different joints that we have. Okay? Here I wrote the name of the joints and the degree of freedom that each joint has, and also the explanation and the way that they rotate. So the first joint is revolute joint. How revolute joint is moving? Revolute joint is rotating around only one axis. It's as you see here. So it only have 1 degree of freedom. Okay? And cylindrical joint. Cylindrical joint allows relative rotation and translation. It means it can go left and right, and it also can rotate. So it has 2 degrees of freedom. The third joint is prismatic. Prismatic is only able to slide up and down, so only 1 degree of freedom. Along one axis, moving up and down, 1 degree of freedom. Spherical joint. Spherical joint allows 3 degrees of rotational freedom about the center of the joint. Okay, there's another name for it, which is the ball and the socket joint. So why? Because imagine this is the spherical joint, okay? It can rotate like this, it can rotate like this, and it can rotate like this. If you imagine X, Y, Z, it can rotate in each one of these axes. So it has 3 degrees of freedom. Planar joint allows relative translation on a plane, translation in this direction, translation in this direction, X and Y, and also rotation around the Z-axis. So this one also have 3 degrees of freedom. Everyone are fine with it?
So now the concept of degrees of freedom, you're moving to a new
Sorry?
topic.
I'm moving to the workspace.
So,
Knowing each joint, how it can move, now we can understand a manipulator, which each one of these joints, what its workspace will be. So we first have to know each joint, what type of motion it has, so then we will be able to understand the workspace. Okay?
so I want just to,
Yes?
I thought about something. So I think there's a differentiation, but there's a link between degrees of freedom when you speak about rigid body,
Yeah.
and there's a difference between degrees of freedom of a link. So each body in the Cartesian space and the three-dimensional space has 6 degrees of freedom. But when we talk about a mechanism, I think the minimum number of parameters which would specifically identify the position of the mechanism would be the numbers of its degrees of freedom.
Mhm.
So, for example, if you have a telescope, so all of the joints are, let's say, prismatic, but they're in the same line.
Yeah.
So the number of degrees of freedom is equal to the number of these extrusions which you could have. But an important issue is that they're not independent. So we have dependent, let's say, degrees of freedom, and we also have independent degrees of freedom. And the number of independent degrees of freedom is something which has to do something with the robot being redundant or not redundant. So the definition of redundancy, I think it spins off somewhere from here. Yeah.
Okay.
Anyway.
Redundancy is you have more degrees of freedom than what is needed
Yeah.
to position the end effector in some point and at some orientation.
So, for example, in the two-dimensional plane, if you have a planar manipulator like that one with 2 degrees of freedom, does not necessarily mean that your manipulator could sweep the entire two-dimensional plane, because
No.
its 2 degrees of freedom might be
that's
dependent.
space. Yes.
I mean, this is
So within the workspace,
yeah.
you can reach any point, and then like you can reach, let's say if it's a 2 degrees of freedom, you can position the end effector at a 2D Cartesian coordinate point by controlling these 2 joints. That's all.
So, for example, in the three-dimensional space where a rigid body has 6 degrees of freedom, your robot might have 6 or even more degrees of freedom, but still not be able to sweep the entire space.
Yeah. No, it doesn't say anything about the entire space.
Yeah.
It says like, so given a point and an orientation, so point 3D and 3 orientations, that is 6. And if they are within the reachable space, then
Okay. So let's move to the workspace. So workspace is the volume of a space that specific manipulator, each specific manipulator has its specific workspace, okay? Now we're talking about, for example, this manipulator. So workspace is a volume that this manipulator its end effector can move and reach these points. So if you look at this manipulator, its end effector can move around all of this space and also inside. So this is the volume that this end effector can move inside it. Okay? So if you look here, this is the fixed, this is a type of like, how I can say, going back to what I said before in order to be able to make sure that you all know about it. So this is a revolute joint, so it has only 1 degree of freedom. It can move in this direction and in this direction. Okay? This is a revolute joint again. It can rotate around. So it will make it able to move from this side to this side, this one too. And this is the prismatic joint, so it moves up and down. So it can reach this point, the maximum, and minimum this point. Okay? So reachable workspace, this I took it from Thrish's slide. I had a bit of problem understanding the reachable workspace and the dexterous workspace. So the reachable workspace is the volume of the space which every point can be reached by the end effector in at least one orientation. It means that the robot, if you imagine this volume is a set of different points, okay? What I think it means is that this manipulator, for example, if we have a point in here, this manipulator can reach this point in this direction and can reach this point in this direction. Am I right?
Yeah, so it is like the reaching is not orientation. Reaching is positioning the point.
Yeah.
So, but if you add at least one orientation to that, then it becomes 4D, right? So this is 2D and then it becomes 3D.
Mm-hmm.
So it's like alpha azimuth, like alpha, beta, or gamma. So you add alpha, right? And then within that workspace, there's another subset of the workspace.
Yes.
You can reach with an alpha, given alpha, and a given position.
Mm-hmm.
Okay. So that workspace is a subset of this workspace.
Could you repeat again the difference?
Okay, so let's say I can reach all these points, right?
Mm-hmm.
So that is my workspace.
Mm-hmm.
But if you ask me to reach that point in north
Like here.
northeast, right? So then I can reach there, right? But I cannot reach, if you ask me to reach here with the southeast, then I cannot reach there.
Mm-hmm.
Okay? So it is within my workspace, but it is not within the reachability space. So the reachability space is the space where I can reach and be in some given orientation.
The textures.
Okay.
Yeah.
So is this your definition? I mean, it's an
These
interesting.
three parts
Really?
are his definition.
Because I mean, it was an interesting point to see that yes, you have a reachable workspace, so you stretch
Yeah.
out your arm and you can reach
Yeah.
anything, but I cannot do much.
Yeah,
once
do
I-
much
I-
with it.
Exactly.
So there is a volume of workspace inside
Yeah.
this workspace.
Yeah.
Yeah.
Which you could. Yeah.
The exterior workspace is the volume of the space which every point can be reached by the end effector in all possible orientation.
Right?
It means that
So I can reach this point with that orientation, like alpha, all alpha, beta, gamma. If you give me any alpha, beta, gamma and a position, can I reach? So that is another smaller subset of the workspace. Dexterous workspace is a subset of reachable workspace. Reachable workspace is a subset of the workspace.
it means that any set of joint angles that is possible to give this manipulator, you still will be able to reach that specific point.
Point and orientation, in
And
all
then-
orientations.
Yeah, I mean, with different orientations, with different set of angles, you can reach that point. Any possible orientation, you can reach that point.
But that means that the boundaries of that volume will not be dexterous workspace.
No, they won't.
No, not the upper boundaries, the lower boundaries are usually dexterous.
Yeah, it might be.
Yeah.
Okay?
So the human dexterous workspace is somewhere here, and then that is where we do all the things like so, and then it is reflected in the number of neurons in the in the motor cortex too, like so. The number of neurons, their distribution is very dense in the dexterous workspace, and then it kind of decays down, like you don't have many neurons in outside the reachable workspace. So because of that, like so, if I am asked to write with the chair like that here, which is not in my dexterous workspace, so but I had to do all sorts of orientations, right? Then what I'll do is I'll pull my chair here. right? Bring the thing to my dexterous workspace.
Yeah.
Where you're comfortable. Okay, next slide. So now we're moving into the position.
This is extremely useful in energy consumption too. So if you effectively robot your workbench, and then the base of the robot is not really designed well, it will reach and it will do things, but energy consumption is very high. Right.
Okay. So if we have a point in a space, which we are reaching to that point with a position vector, okay? And we want to explain that position vector with respect to a frame.
Just something to add.
Yeah?
In terms of system dynamics, orientation and position, there is no difference between orientation and position. They're basically states, and but we have reachability there, which means if a certain state can be reached. So
Yeah. So as a general thing, like basically position is a point concept. It's at the tip. Where is it? And orientation is the whole link and then the
That you're moving toward that. So
Yeah.
you may be able to rotate and then
It's
reach
an
that
axis.
point.
It's basically an axis idea.
But now I'm only talking about a position vector. That's all.
yes.
A position
Yes,
of a
yes.
point
But,
with respect to a frame.
Yeah, but you were talking in like a controlled sort of concept, a reachable
in
system.
dynamic systems, yeah.
Yeah,
well,
the
that's
whole thing
different.
is one state. Yeah.
Yeah.
We will go to that one.
I
too.
mean, mathematically, there is no difference between orientation and
Yeah.
position.
Oh, yeah.
There are some
Yeah, yeah.
states. There are just states, and the system. Some states may be reachable, some not.
Yeah, I did.
But, yeah.
Okay.
But if you want to break it to orientation, and position.
Yeah, at the beginning we have to know every one of them separately.
So physically,
down.
they are distinct because
Yeah, physically, yes.
it's
Yeah.
oriented. If you want, do you want to talk about the point, or do you want to talk about the point and the axis?
Yes, yes.
But
But
can we not define or represent the orientation as a form of presentation, and then we will just have one form instead of
Yeah,
dividing
that's-
into
thing is, and it's not only position and orientation. In a system, there might not be any physical meaning for states, but we still think about if that state is reachable or not. In a system.
In a system, in a general system point of view,
Yes.
whether the dynamic system can reach that state. So it's
Yes.
Yeah. Yeah,
But
you
still,
were
any
talking in
vector
the
has-
controlled sort of control theory,
Yeah,
like
and then you
reachable
have
sets,
controllability,
controllability, reachability, but
Yes.
this is a physical interpretation,
Yeah.
just
Yes.
reaching, really reaching.
Yes.
Reaching out.
Yes. I just wanted to point out to the
Yeah.
general things.
So the position of any point in space relative to a frame, to a reference frame, can be described by a 3x1 matrix. For example, this point P with respect to this reference frame can be described by a 3x1 matrix, which
do you
contains...
understand that?
Yeah.
The reference frame, right? The reference frame is just a coordinate system.
Yeah.
Okay.
Every object can have a reference frame, and you can...
So your x, y, z axis. So that's a coordinate system. That's a frame.
Yes. So then, this position vector can be explained by P of x, P of y, and P of z. But I think this y should be moved here. It should be
It doesn't
here.
matter.
It's okay. It's fine.
No, that's correct.
That's good. It should
That's
be
the right hand
right hand
convention.
orthogonal.
Yeah.
Oh yeah, okay, that's true. Where P is Py
What
and
is the
Pz.
right hand rule? Has to do what's the right hand rule?
Sorry?
Right hand rule.
Okay, this figure will be z, okay? And this will be the axis,
X.
for example x. And then when you rotate it in counterclockwise, is the position side. You imagine that your hand is only able to rotate this direction. It's really hard for it to rotate in that direction. So this direction is always positive, this direction is always negative. And this time we say X is pointing out, Z is pointing up, pointing out. When Z is pointing down, it will be like this. Then in this direction will be the positive rotation, in this direction will be the negative rotation. Okay? Which I will explain that later.
What about for positive XY? So
One,
we just refer
Only right hand.
positive.
Right hand, yes.
yeah, and Y is the other 90 degrees.
So in the positive side, positive way, like so, if your thumb is pointing at the Z direction,
That's positive.
your x-axis goes to Y.
Look,
Yeah.
look at my hand. This is Z, this is X.
Yes.
If I rotate
But
in this
basically,
direction,
Z is the cross product between X
Exactly.
and Y.
Yeah. Yeah.
And then we call this coordinate system a right-hand orthogonal. So all the axes are perpendicular to each other, and the third one is the cross product between the other two.
yeah. The third one is this one.
Yeah. It's important in my tutorial when I want to talk about
Yeah.
the path reference.
Okay.
Okay. Everybody okay with the cross product, right?
So this is Z,
It's a
this is
vector.
X. When
Now,
you
why you
rotate it
use
90 degree, it will be Y.
What's that?
Why we use hand?
It's easier.
It's a convention.
easier.
It's a convention.
easier.
It's people use cork screw thing or.
If you go to a
Yeah.
robotic exam, everyone in the exam is like this, you're laughing at
Or
them.
with
But
a
this is the
screw.
easiest way. This is the chapter 2, so you won't need this that
the cork
much.
screw, right? So that's also a metaphor.
Yeah. But in chapter 3, which we are going to actually calculate each one of the rotations one by one, for each one of them you need your hand to rotate it. You will learn it there perfectly. Here I'm teaching the basics, the translation, rotation, position, and everything like
It's
that
fine.
that you need. Okay?
Right. So ask these very basic questions.
So where Px, Py, and Pz are the magnitudes of the projection of the line joining the point P and the origin O. Okay? Next slide. Description of the orientation. So the orientation of a body in space can be described by attaching a frame reference to the frame reference of that object. Okay? So the orientation of a body in space can be described by attaching a coordinate system to it and then describing the vectors of its coordinate axis relative to the new coordinate axis that we added to it. So every object might have, for example, this cell phone. Imagine it's rotating like this, like this, like this. The coordinate here is the axis of it, X, Y, Z. So this phone has the coordinate itself, which I don't know about it. But I know another coordinate axis, which I perfectly know everything about it. So I just attach this coordinate that I know about it to this coordinate. So the center of this coordinate will be perfectly sitting on the coordinate of that object. This way, I can explain the coordinate system of this phone with respect to my reference coordinate, which I know about it. So this way it will be easier. Okay? So, for example, the coordinate axis of frame B is shown with red, can be described relative to a known coordinate system A. So we know the coordinate system A, everything about it. We are attaching coordinate system B to coordinate system A in order to understand coordinate system B. Okay? But this coordinate, the Z is in this direction, X is in this direction, Y is in this direction. But in my phone, for example, the Z, X, Y, Z could be in another direction, like this. The X, Y, Z for my phone is in this direction. How I'm going to explain that? I'm going to find out I'm imagining each one of these is a position vector, and I will find the X, Y, Z of each one of them. Okay? Then I will make a 3 by 3 matrix. This 3 by 3 matrix is a rotation matrix. Why? Because it shows the rotation of each one of these. For example, we imagine at the beginning we had this coordinate, okay? And then we rotated, for example, around, first we rotated around x, so x was fixed. For example, rotated around z, z was fixed, and only x and y were rotating. So we will have a rotation matrix with respect to z. But in this case, all of them are rotating. So we have to find the position vector of each one of them with respect to A. Here we have XA multiplied by XB. We're explaining
It's not multiply, it's the dot product.
dot. I only say where is XA, XB? Why I can't find it? Oh, okay. So we're starting with the X. So we say XA, XB is the X, PX, for example, PX position of X with respect to this X. Okay?
I think it'll be easy if we take a 2D thing,
Mm-hmm.
2D example, and then rotate one frame, and then we have,
We have it later, but I will explain it here.
and then it's easier.
This is, for example, X, this is Y. Let me tell you one thing. When this is Z, when the Z is pointing out in the paper, if they didn't show you where is Z, they will show it like this. The point is filled, so it means that Z is pointing out. But if it is like this, means Z is pointing inside, it's like this. But when it's filled, it's like this. Okay? So,
That's way.
So in this case, it should be pointing that way, it's fine. No, it doesn't matter. So like we have another frame.
Island like an arrow.
do you want to explain this? You explain it better. Because I'm afraid I have to confuse them.
So the it's fine. It's 1, x2, y2.
Or it's x2, y2.
No, X should be
That it doesn't
there
matter.
and y
It
should
really
be there.
doesn't matter. Let's do it right. And then let's say there's a theta, right? So what is xb, xa, x2 dot x1? What is that?
Means,
So this angle is theta, right?
yeah.
What is that?
Some-
Yeah. So now,
Oh, that's cosine.
the cos, right? That's a cos theta, right? So this is cos theta. And then YB XA, Y2 X1.
Sine.
Minus sine.
Actually, no, it's minus n. So Hasita, can you tell me Y2 dot X1? So just imagine these are unit vectors, right? So really we have to divide this by the norm, right? So just imagine these are unit vectors. So Y2, you know the dot product equation, right? So vector 1 dot vector 2 is vector 1 norm, vector 2 norm, they are cos alpha, whatever they are. Okay? So now just think that this is 1, this is 1. So what is the angle between y2 and x1? Y2 and x1?
Cos 90 minus theta.
90 minus theta, right? So cos 90 minus theta. So what is x2 ya, x2 dot y1?
90 plus theta cos.
Right? This is x2, that is y1, so 9 plus theta, right? And then x2, x1, y1, then x1, y1, right? No, sorry, y2, y1. Y2, y1 is
Cos theta.
Only theta.
y2, y1. Cos theta,
Cos
right?
theta.
So what is the orientation matrix? Cos theta minus sin theta, right? And then this is sin theta, right? Because it's in the second quadrant.
Yeah.
Sin theta. So if you want to rotate a frame in 2D by a theta, this is the orientation matrix. Orientation. If you multiply any vector in the original frame with this orientation matrix, it will be rotated by theta. Okay? So in a general 3D thing, so see the pattern, right? So in the first row, XA, XA, XA. Okay? And then you take the elements of the other frame and X, Y, Z, right? And then YA, 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 X, Y, Z. Right?
Okay. So that is orientation matrix that you of one plane, one reference plane to another reference plane. So when we get that matrix, we can multiply it to any vector that we have,
Exactly.
and it shows that change.
That rotates.
The rotation.
Yeah.
So this is purely rotation.
It's purely
Yeah.
a rotation.
There is no
Rotation.
translation, only rotation.
Okay.
Because the frames are fixed on the same point.
Okay.
They're not moved. We will talk about that later when
Okay.
the frames are also moving.
Yeah. So it is used like, let's say I'm looking at that board, but my body is in another frame, right? So my X, Y, Z,
Yeah.
the body is in one frame, but my head is in another frame, right? And I'm seeing the board, but from this my head's point of view, it is X, Y, right? So I'm looking at X, but in my mind I know my body is on northeast, right? Because I'm rotating that thing in my mind, right? So for a robot wants to know, like, if the end effector is reaching that way, it wants to know relative to my base which way I'm reaching, right? So that is why it has to rotate these frames from link to link.
Here we only have rotation. Later we talk about translation and then our transformation, which transformation is a mix of rotation and translation. So we're going one by one.
Okay.
So now, so we know that rotation matrix is this matrix that Thrish explained. And how we show rotation matrix, so the rotation matrix of frame B with respect to A is written like that, or it's written like that. There are two ways of writing them, but both have the same meaning. So rotation matrix properties. So all the columns of the rotation matrix are orthogonal to each other. That's one thing. The other thing is that
right? Yes. Take that. What is orthogonal pasta?
means they are like this. I don't know how to explain it.
Oh, perfect.
What's that? Perpendicular. Perpendicular, right?
Yeah.
Perpendicular. What is the perpendicular? How to check whether two vectors are perpendicular? Take the dot product if alpha is 90, cos alpha is 0, right? Okay, so the dot product should be 0. So if you take the dot product of these two columns, what happens? So these are basic, but this is really
Yeah.
So the dot product is the projection, right? So dot product of a vector is V1 transpose V2. Okay? So that's the dot product, that's the projection. So if you want a V1 vector and a V2 vector, dot product is basically this projection. Okay? So this basically is the dot product. When two vectors are orthogonal, the projection is 0, meaning the dot product is 0.
Right.
Okay? So you can get that by transposing one vector multiplied by the other vector. Okay? So take cos theta sin theta. That is V1 transpose. Right? V2 is minus sin theta, cos theta. What do I get?
Sine, cosine of theta.
Minus C S plus C S 0. So they are all okay?
Rotational matrix is not only orthogonal, but it's actually orthonormal.
Orthonormal, yeah. What is orthonormal?
The magnitude. The magnitude is 1 as well.
Magnitude is 1, yes. Magnitude of each vector is 1.
It has to be both perpendicular and
And
magnitude.
what is the magnitude of V1? What is the magnitude of V1?
What's your V1?
It's
Magnitude of V1.
Magnitude, okay.
It's 1 because cosine squared plus sine squared is equal to
So magnitude of a vector V is V transpose V. Okay? Okay? So and that's V2. So that is cos theta sin theta times cos theta sin theta, right? Is that right?
Square root? Isn't it square?
Yeah, so it is cos squared theta plus sin squared theta is 1. Right?
Yeah.
So these are orthonormal vectors. These are perpendicular. Yeah, if it is perpendicular, the
cross product.
the dot product should be 0, and then orthonormal, if you take one vector and then take its own norm, it should be 1.
That is
Okay.
orthonormal.
What do you mean when it's its own norm?
Norm is V transpose V.
We transpose it. Okay.
The magnitude of the vector.
Yeah.
So,
Norm is basically Euclidean distance to the tip.
okay.
So the second factor is that the determinant of the rotation matrix is 1, which I explained the determinant here. So the determinant of a matrix A, a 3 by 3 matrix, is denoted as that in parentheses A, that's A or A in. So how we calculate the determinant of a 3 by 3 matrix? If
What is why determinant is important?
Oh,
What does it mean?
that is the first one.
question like Ali's question.
No, then
So let's say you take a matrix and you multiply a vector, and then it goes to a new vector. So what does determinant do there?
I think first if the determinant is 0,
It's
it
the
becomes
area
singular.
gain, right? So it's the area gain
Yeah.
of if the determinant is 1, there won't be an area gain, right? So in terms of stretch.
What's an area gain?
So okay, so you let's try that out. Okay, so you don't believe me. let's take a matrix and then calculate that.
Yeah.
Take a random matrix. A is 0.5, 1, 0.2, 2. Okay? So we have a vector 1, 1. Okay? Now to be fair, let's take 1, 2. Okay. 1, 2. And then multiply this by 1, 2. What do we get? 3.5 and 4.2. Yeah. So it goes to 2.5 and then some. So this volume is 2, right? This original volume of the vector is 2, and then this volume is something. So take the determinant of these vectors. So
0.5
So
It's
it's
1
minus
0.2.
0.2, right?
Yeah, it's 0.8.
It's 0.8. So 0.8, and then this is 2, right? 4.2 is a magnification.
Almost 2 times.
2 point something.
So 2.5.
It's more than 0.8 gain, right?
Yeah.
Yes. It's
Little bit.
almost 2.
It's almost double.
Yes.
It's more than that.
More than double.
Yeah.
So basically, that V times determinant should be this one. Is that right? Can you check the
So 2.5 multiplied by 4.2 to
Yeah.
get the area
yeah
is 10.5.
10.5?
Yeah. Divided by 0.8, right?
No,
That's
multiplied by this determinant.
multiplied by, how much was the determinant?
0.8.
5.8
minus 0.2.
is 8.4.
8.4. Sorry, I think. So the. Hold on. So the area swept by the vector. I think that
It's
is
the area under the vector, so the problem is
Area.
that area is not 2, it's 1 because it's a triangle. So underneath that triangle for the smaller
This is
vector,
1.
and then we need that area.
But it is
of the other
just half.
triangle.
just half of that. Right. So area swept. Can we calculate the area swept by this? Area swept by this. So this is that total area, right? So can you take
10.5.
10.5?
Yeah.
So that is the total
Area.
square.
Yes.
And then triangle is
Divided by 2 is 5.25.
5.25, right?
Yeah.
And then this triangle we had originally is 1,
Originally 1, yeah.
right? 1. So, and then we had to take away from that big triangle this area. How do we get that area? You know that the thing, right? So this is 4.2. This is 2, and then this is 2.5 minus 1. 1.5, right?
Yeah.
Okay?
Yeah.
So then that area is
2 plus 4.2
2 plus 4.2 times 1.5 divided by 2. Right? Can you get that?
So is that
2 plus 4.2 is 6.2.
6.2
Times
times
1
times 1.5.
1.5
1.5 is
divided by 2
divided by 2 is 4.65.
4.65, right?
Yeah.
Now take away from 5.25,
5.25,
take away 4.65,
0.6.
right? Take away this,
It's 0.6.
6.6.
0.6. We should come to 0.8, right? We should do it.
We're almost there, yeah. Very.
You almost did it.
And add 0.2 to it.
No, so somehow, right?
Well,
So-
I think you should, for a triangle you have 3 points apart from the origin. You have to transpose both points, not just 1 point. So 1 point is 1, 2. The other point is, if you're talking about the area under that vector, it is 1, 0.
Yeah.
So we have to transpose 1, 0 now as well.
There
That
is
doesn't
another
matter.
issue with this one.
Doesn't matter,
The
right?
square matrix that we chose is not collinear. So if you have that's the column, the horizontal 0.51 is not collinear with 0.22. So we are not going to get, the determinant is not going to give us that, I think.
No, that's linear. You know, that's anyway a matrix, and it's linear transformation on the points.
The whole matrix is but
Let's work it out.
0.5
Let's work it out
and
later.
1
I think so.
This is
Somehow
and 0.2.
you should
I
give
think
us
there is
the
something
area
I will
swept.
find that and I will send it to you.
Yes.
Area
Doesn't
swept by.
Yeah, it was-
Anyway, but the thing that you said is correct. You said a determinant of a square matrix with real entries, so there is no need for it to be orthogonal or anything else. It gives the scale factor by which the area or volume is multiplied.
The area.
Yeah. So area we
Under
gain
basis.
basically.
Yes,
Area we gain.
And I remember we calculated the volume of a pyramid using a 3x3 matrix.
Yeah.
So, yeah, that was correct. But I think you have to.
No, we made a mistake somewhere there.
Yeah.
So we have to calculate it later. So it's really important, the physical meaning of
Yeah,
the
yeah.
determinant. It is like, so when you rotate a vector or scale a vector, what kind of area we are gaining?
Yeah.
So that's the
Yes, yes, and that's the thing. I think you have to transpose
Do you want to give it another try?
1, 0 as well.
I have
So
an
how
idea.
to try?
I have an
Okay,
idea.
it's
Calculate it later and then bring it up.
Yeah,
For
the
the
thing is,
slides, I'm going to teach you.
Oh, okay, fine.
Okay, it's
It
on
is
the
included.
And the point of a pure rotation matrix, determinant being 1 is it does not scale the.
It doesn't scale,
Yes.
right? Exactly. Right.
It just rotates.
It just rotates. Yes.
So the other factor for rotation matrix is that the inverse of the rotation matrix is equal to its transpose. Okay? So this means that the rotation matrix of frame B with respect to frame A is equal to the inverse and also the transpose of the rotation matrix of frame A with respect to frame B. Okay? Which will be this formula. So rotation matrix of B with respect to A is equal to the inverse of the rotation matrix of A with respect to B equal to the transpose of rotation matrix of A with respect to B. Okay? And the formula for transpose is this. So the transpose of matrix A is denoted as AT, and then how it works is that this is the row, the color? Okay. The color will become the row. This color will become the second row. This the color will be the third row. That's the transpose. How we calculate the inverse? In the inverse, we make use of the determinant. So the inverse of A is equal to 1 over the determinant of A. Okay? Multiply by,
The adjugate matrix.
yes.
Adjoint.
We write it as ADG matrix.
Adjoint is the transpose of the cofactors.
Okay? Now let's move to the rotation about z-axis. So, at the beginning I explained that the whole frame is rotating with respect to another frame. Now we're going to fix z-axis and only rotate the other frames. How it works is that the reference frame of A, the Z in the reference frame of A is in the same place as the Z in the reference frame B, and only the X and Y are rotating. How it works? Like this. If I rotate it for alpha angle, it will be like this. X of B, X of A will move to here, X of B, and Y of A will move to Y of B. Okay? So, in the reference frame or frame A, if a reference frame or frame A is rotated by an angle around the Z-axis to obtain a new frame named frame B, the rotation matrix of the new frame is this. So, we say the rotation matrix of B with respect to A, because we rotated B with respect to A, is equal to cosine of alpha minus sine of alpha 0. I always memorize it, so, but if you want, you can calculate it through this, as Thrish explained before. But the best thing is to memorize it. So the rotation matrix above y-axis, and this time we are rotating around y. It means y is not changing, and only the z and the x are rotating. Y will stay the same. It will be like this. Okay? So then the rotation matrix for the reference frame B with respect to A, around, which is rotating around Y for the beta angle, it will be this. So in this slide, we're rotating around X, means X is going to be fixed, and the other axes are rotating. So the rotation matrix for it will be this.
Why should that be 1? So first element should be 1.
Because it's rotating
Around X is same.
So XA dot XB is 1, right? Because it's in line, so cos 0 is 1.
Exactly. If you go back, here, YA cross YB is 1.
Yeah.
And the previous one, ZA cross ZB is 1.
Dot.
Dot. So what is that now? We know about the rotation matrix for X, Y, Z. Now we move to the cascade rotation. The final orientation of a three successive rotation made about moving axis is the same as the final orientation of a three same rotations taken in the opposite, I will show you the photo, in the opposite order, but on a fixed axis. These are the same. What does it mean? If you look here, this frame is rotating around Z, okay? Now we will get a new frame. Then, with respect to a new frame, we will make a new rotation. Then we take the new frame, and then we do a new rotation, okay? So, here, we rotated around Z, around Y, around X. And the frames were changing every time. Okay? This is equal to the orientation of this tree, the result we get at the end, is equal to what? If you look here, this frame is the same as this frame, is the same as this frame. The basic and the initial frame is the same for all of them. Here, we rotate around X. This is our new frame, but we leave it here. We have the same base here. Now we rotate the initial base around another angle, around Y. And we leave it here, the new axis. We again take our initial axis and we rotate it around Z. What is the difference between these two? Is that here, every time we take the new frame after the rotation as an initial frame for the second one, or the third one, okay? But here the frames are fixed. So the orientation we get as a result of this rotation with respect to the new reference frames is equal to the orientation we get as a result of multiplying the rotation axis on the opposite side, the other order. Here, we say rotation matrix of this multiplied by rotation matrix of this multiplied by rotation matrix of this will give us a new rotation matrix. That is equal to the rotation matrix of this multiplied by rotation matrix of this multiplied by rotation matrix of this. However, we change them in this order, but when we want to multiply them, we multiply them in this order. Why? Because here the reference frame every time is changing, but here the reference frame is always the same. So the rotation matrix of B with respect to A, when the reference frames are moving, is equal to the rotation matrix of B with respect to A when the reference frame is fixed. If you look, the angles are the other way. Alpha, beta, gamma. Here we have gamma, beta, alpha.
So for a two-link or three-link serial robot, which one usually we use?
It depends. I can't say. It depends how that manipulator is
Which-
moving.
I mean, we know that the next joint is rotating with respect to the previous joint. So which one is easier to use?
So if we have it.
So we just use the final alpha beta gamma thing. So we use one transformation.
Yeah, but to drive it, do we do post multiplication or pre multiplication?
I think.
I think we do this one. This one. No.
Could I add
We
something?
do this one. Because sometimes they're moving. We don't have the same rotation in the next one. Because what we do is that this has one reference frame, but this one has another reference frame.
Okay.
And this one has another reference frame. When we want to find out the translation or the rotation for this one, okay, we first write the rotation matrix for this, rotation matrix for this, rotation matrix for this, but we multiply them in this order. This rotation matrix multiplied by this rotation matrix multiplied by this rotation matrix. Because every time this is with respect a new frame. This frame is not same as this one.
So do
It's
you
changing.
understand? Everybody understand what she means by frame here
Sorry?
in the manipulator case?
So
Can what is a frame on the link?
So I think let's just add some little thing is that first we have a body attached frame and an inertial frame, so let's first distinguish between these two. So the body attached frame, as you were saying, is the one which is attached to the cell phone or to the body, and you have an inertial frame which is always fixed, let's say. Secondly, the rotational transformation matrix has, in my opinion, three interpretations. The first interpretation is it takes frame A to frame B.
Yeah?
Second interpretation is it takes point.
Yeah, take a 2D, two-link case. You can use that. So for the time being, you can assume Genevieve-Hardenberg convention, which is the z-axis is always in the rotation axis,
Yeah.
right, in the motor, right? So z-axis is coming out of the board. And then the x-axis is along the link.
Yeah. That will explain it in chapter 3.
Oh, you do, right.
I have this in another slide. You can explain it through that. Yeah.
Yeah, but this, I just wanted to talk about the rotational part, not about the translational part. So a point in space could be represented in any coordinate frame. It could be in the inertial coordinate frames, or in a body attached frame, or a third frame. Now, a rotational transformation matrix, let's say, if I call it from frame 1 to frame 2, does three things in my opinion.
That is, sorry, frame 2 to 1, not 1 to 2.
So I'll get to that. And the first interpretation is that you could view it as rotating from frame 1 to frame 2. That's so rotation of frames. The second interpretation is that if you give a point in frame 2 and multiply it by this matrix, it will give you the coordinates in frame 1.
Yes.
So let's call it, I don't know, a transformation of a point. The third interpretation is that in the same frame, in frame 1, if you multiply a vector or a point by this rotational matrix, it gives you the position in the same frame, but after the multiplication. So it just means the rotation of the point in the same frame. So let's just call it rotation in the same frame. So in a manipulator, when we want to go from, so for example, if this is frame, let's say 0, then this is frame 1, and this is frame 2, frame 1, and frame 0. So if we are translating along the manipulator's arm, and if we want to achieve the final position, what we do is we do a concatenation of multiplication. So we multiply 0 to 1 times 1, 2, and so on and so forth if we have more, 2, 3. So with this multiplication, you can multiply the coordinates of the endpoint represented in its local frame, let's say in the third frame, and it would give you the coordinates of the endpoint in frame 0. Just a summary of what I understand.
Okay.
To be.
Yeah, but it's still sort of sitting on your place. What I said before, yours is one of that situations. What I said before is that it's not always the same thing. Sometimes the second frame is totally different with the first frame.
In this case,
In this case, what I'm going to say is that
Of course, assuming all of them are rotations, now this has a translational part too, which
Yeah, of course, yes. So basically, what it does is, so you have two manipulators, right? So right?
more.
And then so there is this direction, right? That vector, and then look at that vector from this frame. It is along that x-axis, right? Okay. Look at that vector from this frame.
yeah.
This frame is in that direction, right? So meaning how this frame sees the vector has to be rotated by some angle when it comes to here, right? And then he sees that as that, and then from this frame it is a vector like that, right? So basically, what frame is seeing that thing, which way, is the question. So rotating and then translating. So basically, finally, we have to have, okay, so that's where it is, and then that's where it is pointing at, looking from this. But we don't know, right? We have to do that by back propagating that vector through the whole link.
So
that is
what we
are-
wrote here is exactly what will happen in the beginning and at the one above. This one is when you have an object, you rotate it, and then you bring it back to what it was before, and then again you rotate it another direction, you bring it back to what it was at the beginning, and then you rotate it another time. We mostly have that occasion happening, not this one. This is just for your understanding.
So just to sum up what Thrish you mentioned and Ali, can we say that we can actually have one universal frame,
Yes.
call it, which is, let's say, the physical space in this case
Yeah.
that we see in front of us for the machine?
Yeah.
And then for each of these, the manipulated joints or the
Yeah,
endpoints,
yeah,
okay, joints,
Yeah.
we are going to see a vector transformation relative to this universal,
Exactly, yes.
and then the multiplication is going to give us the resultant vector
Yeah.
from the
So we
original.
have to use these multiplications because we don't have a camera looking from the base at the tip, right?
Okay,
Then
yeah.
if we have it then we are solved. So what we have is joint encoder readings,
Okay.
right? So then we have to use the joint. The only way to use joint encoder readings to look at the endpoint is to do these rotations frame by frame.
Okay, sorry, I missed the part. So, using joint encoders, which one of these two we can use with?
We
with
always
every-
use the one above.
the
This
above
one,
one, right?
just, yeah.
I just wanted to make that point.
When we select the frames, we isolate one frame and go for another one.
Yeah, so that's isolate
Yes.
the frame. So she will talk about how to assign frames. There's a convention called the dynamic Hartenberg convention. So that tells you exactly how to assign these frames, which way the z axis should be pointing, x axis should be pointing.
So here, mapping involving rotated frames. In here, in this situation, we know that the position vector of the detail about the position vector PB, okay? And we want to know what is this position of this point with respect to frame A when both frames are fixed on one point. So frame A starts in this point, frame B is on the same point. We know position of B, position of this point with respect to frame B, but we want to know position of this point with respect to frame A. And this time, what we'll do, we'll use this formula. We say the rotation matrix of B with respect to A, because at the beginning we had A, and then it's rotated, and it becomes frame B, okay? So we say the rotation matrix of B with respect to A, multiplied by this position that we know, it will give us P of A, the position of this point with respect to frame A. Okay? What I always do, sometimes we have many rotations multiplied to each other and then multiplied to a position. What I always do is that I will cross this one with this one. It will be A left, so then I will say the position of A. I got that. If you have many rotation matrices multiplied to each other, you cross this one with that one, this one with that one, with this one with that one, then you know that you're multiplying them in the perfect order. That's my way. So this is the basic. So this is for when the frame are fixed and they are rotating, and we want to know the position vector of one point with respect to the second frame. Done? Now, we have an example. Figure below shows a frame B that is rotated relative to frame A. They're still on the same point, okay? Above the z-axis by 30 degrees. We know the rotation matrix, the formula for rotation matrix rotating around z, which is this. The rotation matrix rotating around z is this. And we know the position vector of B is already known. And now we want to find the position vector of A. So first we have to calculate the rotation matrix. We know that the rotation matrix is rotated with respect to Z for 30 degrees. Using this formula, we will get the rotation matrix. And now we can calculate P of A, position vector of this point with respect to this frame will be equal to the rotation matrix of B with respect to A multiplied by position vector of B, which will give us P of A. Means the position vector of A with respect to frame A.
Good.
Now, the mapping involving translated frame. Now, the frames are not rotating. They are only translating from one point to another point. What will happen in this point? In this point, we have to also take into account the position of the origin of two frames. This also has to be added in our calculation. Because this frame has moved from this point to this point. But the frame is still the same, it's not rotating. So this vector will be the position of B origin of B to origin of A. Okay? So now P of A will be calculated by summation of this vector and this vector. Because we didn't have rotation. Now what will happen if we also have rotation? We have translation and rotation. At this point, we say the position vector of A is equal to the rotation of B with respect to A. Frame B has been rotated, yes? And also has been translated. So we have to find the rotation of this frame, B with respect to A, multiplied by the position vector of B plus the PB of origin. It will give us P of A, position vector of A. Okay? In another word, the multiplication of the rotation matrix and the position is the translation, which we show it by T. Transformation, sorry. Translation means moving from here to here. But when we have rotation and translation, we have transformation. We call it transformation. So if we want to, like this is a matrix, if we want to start calculating, we will put it into we should make this into a 4x4 matrix, which in here, we write the rotation matrix of B with respect to A, and then here we put the P of origin with respect to A. Here we have to put 1, 0, 0, 0. Then the position vector of B, we have to put 1 here too because this is 4x4, this should be 4x1 too. That will give us the position vector of A. That is the way we calculate it. Okay? Done? So now example. Figure below shows a frame B which is rotated relative to frame A about Z. Means rotation matrix of B with respect to A around Z for 30 degrees. And also translated 10 units in XA and translated 5 units in YA. Find PA where PB is, here it has a problem. PB is 3, 7, and also 0. I wrote it here, I have it. So we know that it has been rotated around Z for 30 degrees. Using this formula, we can calculate the rotation matrix. And then we will put the rotation matrix in the previous slide that I showed you in here. We put the rotation matrix in there. We know the PB origin, and they also gave us PB, so we can calculate PA. Okay? So now, translational operation. This slide is something same as what I explained before. They just say that if we want to move this position vector to here, okay, then we can, and we want to calculate P2A, then we can say this vector plus this vector will give us this, okay? But we can also write it in another way. We can write it in a rotation matrix. We can write it as a transformation matrix, which, because we didn't have any rotation, the axis wasn't rotating, it's the same, so here the rotation will be the identity matrix, and here will be the position. That's something. stupid. This is the same. Okay, we already explained these examples. Okay, what will happen if if it's become more complex? We have many translation and many rotation. What will happen at that point? So here we have this frame, which then this frame has been moved here without any rotation. So we have the reference frame B, and then this reference frame reference frame B, not only rotated, but also it's transformed too. So how we're going to calculate that? If, I don't know if I can write on this, no I can't. So, if from this point till this point, what vector it will be? It will be the position vector of B from this frame to this frame, to this point. So from this frame to this point is PC. From this frame to this point is PA. So obviously from this reference frame to this point is PB. Okay? If we want to calculate PB, it will be what? The transformation of C with respect to B multiplied by PC will give us PB. And if we want to calculate position vector of A, we will say the transformation matrix of B with respect to A multiplied by PB, the position vector of B, will give us PA. That's another way of finding PA. So now, what if we want to find PA through all of these three frames? Then we say the transformation matrix of B with respect to A multiplied by the transformation matrix of C with respect to B multiplied by the position vector C, it will give us PA. Okay? And now, we know that what I told you before, if you cross this B with this B, it will be the transpose of C with respect to A. So instead of this, we can write the transpose of C with respect to A. Okay? And how we write it, if we want to write it as a matrix? We will say the transformation of C with respect to A is the rotation matrix of B with respect to A multiplied by the rotation matrix of the C with respect to B. So here we will have the rotation matrix of C with respect to A, yes? And here we want the position P of C, position of C origin to A. No, sorry, we need PA. So here we found the rotation matrix of C with respect to A. Here we want position of A.
So you can be easier to do cascade multiplication of two transformation matrices.
What do you mean cascade?
So let's say if you write first write T1 is T1.
T1
is RAB BORG.
Sorry?
So if you go back to the slide, so
Stop.
oh yeah, that one. So ARB, so you can write. So that one.
I should write that
Basically
one?
that one, yeah. A set.
Okay.
So then write then
For that one, I should
it's
write
B to C. So that is B to A. So C to B.
rotation matrix of C C to B multiplied by rotation matrix.
No, just one rotation.
Oh, only C to A.
Yes. C to B, C to B.
C to B.
And then B, so PCORT from
PC.
frame. From frame B. That's right? One. Okay, so now that point is in the C frame, right?
Yeah.
Okay, so
Yeah.
then you multiply this translation matrix by that transformation, then you get that.
Yeah, we'll get that one.
Yeah, so can you multiply?
Yeah.
Two?
But this one is not PA.
Yeah, that is
one
PA.
will be-
That is PA, that is PB, that is PC.
This is PB. And that is PC.
Yeah, because, yeah, exactly.
Yeah. So if I multiply these two,
Okay.
we will have the rotation matrix of B with respect to A multiplied by rotation matrix of C with respect to B,
Yeah.
0, 0, 0, 1. And here we have the PB origin, PC origin, PC origin with respect to A, plus PB origin with respect to A, which we had in something else.
Multiplied by,
Multiplied by rotation matrix of B with respect to A. What's that? Oh yeah? Yeah, it will be that. Then these two together will be the position of the,
PC, and then output is PA.
because these
No.
two,
Yeah, so you multiply that by times PC,
yeah?
and then your output is PA.
Oh yeah, you're right. So this will be PA,
Right?
yeah.
So see the pattern, right? So when you cascade multiply these transformation matrices,
Mhm.
what you get is like rotation matrices multiplied, right?
Mhm.
Pure rotation matrices multiplied. RB, PRC, you can go on and on. And then the origins, right? See, A, B, B, and then AB. So A, B, C, A. Right?
Wait, this one has to be.
So your base,
This multiplied by one matrix should be PB, PB, PC. Yeah?
yeah.
So about that.
Okay, so that's the pattern.
So, end of the slide. So, Euler angle, the representation describes an orientation using a set of 3 successive rotation about moving axis. Means that every time we work on the new axis. So here we rotate around Z for about alpha, and then we take the new axis, we rotate around Y for about beta, and then we take the new axis, we rotate around Z again for around gamma. Then the resulting rotation matrix of these 3 rotations will be this. So rotation matrix around Z for alpha multiplied by rotation matrix for around Y for beta multiplied by rotation matrix around Z for gamma. When you multiply this, you will get this a 3 by 3 matrix. And then if you want to find the angles themselves, if they give you the rotation matrix already, they already give you each one of these rotation matrix, and you want to find what angles they've been rotated for, then you can use this formula. Okay? And we have another set of rotation, which is roll pitch yaw, which is around z by x. Roll is z or roll is x?
Roll
Roll
is around z.
z. Okay. So here, this representation described a rotation using set of 3 successive rotation about fixed frames. So then the rotation matrix will be this. So if you see, we multiply them in another order, in the other side. So it rotated around x, and then y, and then z, but we will multiply it rotation in the other way. Rotation matrix z multiplied by rotation matrix y multiplied by rotation matrix x. And if you want to find the rotation matrix will be like that. Okay? And if you want to find the angles themselves, if the rotation matrix are given and we want to find the angles, we can use this formula. Thank you.
Great.
This is chapter 2.
Cool.
Very, very basic. And then next chapter will be
Chapter 3, which is kinematics.
kinematic.
The Dunning-Tardenberg conversion. So once we have done this, rest is easy.
Yeah, now that you know this, the rest is
Frame assignment. And
just a
this.
table of different angles, and then
Yeah, taking just.
I think with one example it will be finished, and then we'll go for Jacobian.
Yeah, okay?
So, Thrish,
Yeah.